So alternative ways, as I mentioned, I only talked 3, but there are more, okay? So one is what we call the continual reassessment method. And this is Bayesian, what we call adaptive design. So this typical, so that's why it's depend on model, but most of those models only have one parameter. So therefore you have some kind of relationship. So one most common one that used is called power model. So I apologize for this notation mess up again. So the power is basically so the pi underscore I is the toxicity rate at the dose I, okay? So the toxicity rate here is an exponential function. So basically it's a constant called AI that corresponding to that dose, but then to the power of the gamma, okay? So it's you can think about 2 to the power of gamma for those one. The other one is 3 to the gamma, and the next one may be 5 to the gamma. So you need to pre-specify for those one what that number AI is. What's really interesting is the power function, that the gamma in the power part. That is a random variable, which depends on your treatment. And that one, we have a prior distribution called exponential distribution. And in order to determine those AIs, or the constant that you're going to do, and one way that you can trick that system is to guess what toxicity rate will be. Then you draw a line, take the log of toxicity rate, draw a line, see which will be the closest line to that, and that gives you some guess about AI. But it's not very intuitive. The other way that we do is logistics. So basically you get logic, which is the log of pi divided by log of 1 minus pi. So the log are the odds. So it's a log of pi over 1 minus pi. So the log of the odds, which is a linear function of those. So in this model, basically the unknown parameter are the 2. One is intercept, but the one that associated with those is the regression beta. Okay, so these 2 are random variables. And then as Bayesian, when you say random variable, you have to define distribution. And so the prior distribution, which you haven't do experiment, is your guess, how they behave. So usually you can specify alpha beta as a uniform distribution or as a normal distribution, depends on the preference, but both are the options. So these are the parameters that you need to give the clinician, to the statistician. And once you have that, you can run standard Bayesian method. So the Bayesian adaptive design, I will show a little bit about comparison later. So I just take my word right now, summarize. It's much better efficiency, and you use, so basically because it's curve data, so everyone will contribute to the overall curve determination. So you're no longer only contribute to your cohort. And also, it's more efficient because every one patient contributes. So you can move, just one patient, you can move to the next dose. And most time, you will allocate right MTD. Of course, maybe sometimes it's too aggressive, and therefore there's rules that you want to make sure modify CRM, that you don't jump those levels. And also, it works for any cutoff values. You can look for the MTD for 25% toxicity rate instead of just only 1/3. But it's not very popular for whatever reasons. One thing, difficulty is the parameter to specify. As I explained earlier, in the power model, you have to specify your constant before the power function, and which is hard to explain. And also the computational burden, which in the old days is a problem, but now it's less because all these web and software are much easier to get. And the other real concern is the review committee. The product review committee may not understand it, and you get more scrutinized. So on the other side, so in order to avoid that you have to specify too many parameters and to get more intuitive, this is called the modified toxicity probability interval method was a good alternative. And basically, the reason of that, it's different from previous that you set a toxicity threshold. Now, in this MTPI approach, you actually say, this is my target, okay? I can be 0.3, 0.25, this is my target. But realize that those never be a constant, so in the toxicity rate, it never be constant. So I can give a range that I feel it's acceptable. So for example, if my target is 0.3, I can have a range of 25% to 35% being the range acceptable. Then you say, I have how many patients that I have, okay, for each cohort. And then you say, okay, here's the program that those group that I will be tested. So the nice part of that, it's rule-based. The rule, where's the rule? Rule will be generated by a software. And all you do is based on the map, okay? So here is the rule. So the mathematics behind that is, I can skip that, is a Bayesian calculation. So here's the website. So this is the website that you can get publicly, everyone can get in, that will be provide the design map, but also calculate MTD. So here's an example that I entered. So once you log in, there are two interfaces. One is put your design. So what you need to specify, your maximum cohort size that you can specify. And then what is your target toxicity rate? Okay, so I put 25. Then what is your lower bound? I say 2.5%, and the upper bound 2.5%. So once I enter that, it's create this table for me for each cohort. Basically, this is the escalate rate. So that's how you go move up. This is the stay, okay, which means you continue at the current state, and there's a de-escalation. You can say, okay, this is too high. I want to go the dose before. And anything the red, just say, never test this dose anymore, which is much harder. So we read this table as these are the number of patients already in the cohort. These are the number of toxicity that you observed, okay? So for example, if I have a patient, for first patient account with 0 toxicity, I continue. I escalate to the next dose group. And if I have the 2 patients with 1 toxicity, I stay on course. So something like that. So that's how you read this table. Now this table is already incorporated your target probability, your threshold, and also once you've done the trial, you can put into, say, for dose group 1, I only have 1 patient and tested, which have 0 toxicity. For the group 2, because upward, forward, I actually tested 7 patients as with 1 toxicity. Those groups 3, I have 6 patients tested, 2 of them have toxicity, and so on. And then this algorithm gives you the recommended dose, which is dose group 3 as target 0.25. So there are a lot of math behind this, but this is very easy and accessible. And actually, this is one of the simulation study by the group that the people use the website, enter their trials. So the nice part of this software is give you the MTTI design, but also give you power model for the CRM. And they show that most time that this is the difference of MPTI versus 3+3 and CRM versus 3+3. And virtually, so this is the meeting, how many times that recommend the right dose, okay? So you can see 3+3 always under recommendation. So most time, both MTPI and CRM recommend right dose more often, and there's virtually no difference between the MPTI and TPI and the CRM. Now these are the number of patients actually on the right dose, because you want give the most patient to be on the safe dose. And you can see, again, virtually no difference, okay? And slightly, if anything, slightly upward. So it's better algorithm for that. So I try to introduce 3 methods. You perhaps don't need to know the details how they do, but there's a website available, and it's very easy to use. So that's what I would suggest you. If you really want to avoid the models, you go to MPT, modified toxicity probability interval as the alternative 3+3. But there are obviously other ways to do better.